All right, welcome back. Let's go and finish these algorithm analysis slides now. Now that we know all about big O, big omega, big theta, let's apply them to actual algorithms some more. So this is where we stopped last time. So let's pick it up here. Let's talk about worst case, best case, and average case. So these are three different ways that you can analyze an algorithm. The asymptotic complexity of an algorithm, how fast it's going to be, how much resources it's going to use. Usually the one that we care about most is the worst case. Like, what is the longest that this algorithm could possibly take to run? Like, that's when somebody, like your worst enemy, is picking what happens inside of your program, the kinds of inputs that you're getting when nothing is going your way and you end up taking the most amount of time / space to do your thing. And this is what I care about you knowing in this class, okay? Worst case algorithm analysis. That is also what we talked about in 41. Okay, there's also best case. That's when, like, the fastest your algorithm could possibly run, when everything is going your way, and you end up like maybe being constant time for some special inputs. Who knows? And then if you like look at the in-between of these two, you get the average case, and that's when you think of mathematically every possible outcome that could happen in your program, every possible input, and you just average together all of those and see the runtime, see the memory usage in the average case. So this is a more complicated topic. I cannot do it justice in this class. You have to wait until an upper div class, like an algorithms class, to really get into average case analysis, but I'll give you a flavor of it on this slide at least. But this is not something that we're going to care too much about in this class. So let's do these for an algorithm that we know and love. Let's do it for BST search. Okay, so here's a binary search tree. It's got a root. And let's say we're looking for something, and we want to figure out the worst case running time for binary search tree search. What is it? Well, the worst case is if the tree looks something like this, right? Boop, boop, boop. The tree only goes right ever, right? The tree is a list, essentially. It's a linked list, secretly. Let's just say list. And in order for it to be the worst case, the tree looks like this, and the value that we're looking for, like, we get down to here and we try to see if it's it, and it's like, no, gotta go right some more. Oh, sorry, it's not there. And the value's not there. So the tree is a list and the value is not there. That's the worst case. Let's just say value not there to save room. So that's the worst case. And that means you have to make compare with this, compare with this, compare with this, compare with this, compare with this. Go right one more time. You have the null pointer, compare against it. That's n plus 1 comparisons, where n is the number of nodes. And so this would be theta of n, right? Worst case running time, you have to visit every node in the tree, sadly, for BST search if your tree is ugly like this. In the best case, let's think about the best case now. So when would things go our way? What's the fastest that this code could run? So if the value that you're looking for is, in this example, 8, you would find it immediately. You only have to make one single comparison, and then you just return, oh yeah, here's the pointer, I found it. That is constant time. That's the best possible case. That's the fastest this program could run. I hope that makes sense. And then if you average together every ugly looking tree, every slightly okay looking tree, and you search for every possible value at every possible location, it just so happens that the average case running time kind of approximates a loosely balanced tree, and search becomes logarithmic. Okay, so this is same as a balanced tree case. The average case of a BST search is logarithmic time. Okay, but you definitely need some mathematical tools to go and prove that. Let us now that we have some practice with it, let's try doing this for code that we've already written, right? Let's do it for is prime. You remember that one? So what was that? That was like you search for I equals, starts at 2, go until like the square root of the number you're trying to find if it's prime, x. And then what you do inside of that loop is you check, right? Check if I divides x. If so, we found a factor. That means it's false. Return false. Otherwise, return true. I guess I'm using capitals. Return true, something like that. So that's the algorithm. And well, let's try and analyze this. How many operations are happening here? What is the work? So this loop is going to iterate essentially square root of x times, right? Square root of x times, and it's doing this much work inside of every iteration, which is at most like check if it divides something, so that's like one operation, and then return false, that's like another one operation. So in essence, the loop is doing at most square root of x times 2 work, and then you got like a return true at the end if you do that too. You won't ever do both returning false and returning true, but I mean, this is a higher level analysis. It's still going to be the right answer. So in the very worst case, if this ever happens, you do square root of x times 2 plus 1 operations, and that is, of course, theta of square root of x. So there's a square root in that. Isn't that cool? So finding if a number is prime, that takes on the order of the square root of that number, because that's how many numbers you have to search through to confirm that none of those divide it. Okay? So that's some code that we've written already. Let's go back to calculate pi now, given a number of darts. And the number of darts was how many times you iterated, right? How many times you threw something. So there was always a loop that was like, do this following thing num darts times. And then I'll indent, do all this stuff. You got to pick a random number. Pick a random x, y, and then check if that coordinate that we just found is inside the unit circle. Check if inside unit, I'll draw a circle, and then if so, add it to count. And then you did something like return, what was it? X over y, like your counts, and then times 4 or something, because that would give you pi over 4, and then times 4. It's not that original x or y. Let's just say a or b. You have some numbers to divide and multiply. Okay, so let's analyze this. So what is this all work taking? What's the amount of time that this inner loop is going to, or sorry, this loop's body is going to run? It's like, this is constant work. This is constant work. It's an if statement. This is constant work, the body of that if statement. So this whole thing, this whole body of the loop is constant time. And so is this, constant time. And so really, the bottleneck is doing constant work num darts times. That's just num darts times 1, essentially. So that is theta of num darts. That is our algorithm. So it's it's linear in the number of darts that we throw, which makes sense. You do constant work for each dart. And then finally, I gave you this answer already, but let's talk about it. It's sat-solve. Sat-solve a given formula, and it was always about the number of variables in that formula, because we had to try them all. You remember that? So let's say there were like 3 variables in our formula that we're trying to sat-solve. Well, you got to try all the possibilities. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, all the way down to 1, 1, 1, which is, for 3 variables, that's 8. And so if you generalize this, you have to try where there are n variables in the formula, let's say, n variables, let's say has n variables. You have to try 2 to the n possibilities, and for each possibility, you then look at the formula and you kind of run it and see if it gives back true or false. And that's going to take constant work. Okay. So for every different possibility of variable values, we do constant work, and that gives us theta of 2 to the n time. Crazy. Oh, and oops, I've been drawing this in green. Let me draw it in green now. Theta of 2 to the n. Wow. And so this is the hardest problem of the 3. That takes a whole lot of work as the number of variables gets larger. So this is a much harder problem to solve than the other two combined. So hopefully that's making some sense. That's how you do it. We're just getting more practice with it. And yeah, let me show you this cool table that I stole from your book, just to show you how horrible 2 to the n is, an algorithm that's 2 to the n time. So let's think about this. Let's pretend that one instruction inside of a CPU takes 1 microsecond to execute, which more or less is true still these days. Maybe a bit faster with the cooler machines, but this is mostly accurate. And so here we have a function that's supposed to represent how fast an algorithm grows, how much time it takes. And then here are some inputs to that. Like here's the input size, maybe 100 things, size 1000 vector, size 100,000 vector. And here's what happens. Logarithmic time, not even a second. Super fast for all those giant values of n even. Linear time, still not too bad. Still doesn't take a whole second even. N log n, sorting for example is n log n. That to sort 100,000 things, it only takes a little over a second. That's pretty nice. But now once you get into polynomial time, the second you have a lot of input, it takes a while. It takes hours to run an n-squared algorithm on a large input size. It takes days to run a cubic algorithm on a large input size. So 3 nested for loops, you are stuck for a while if you have large input. It takes years, right, if it's 100,000. And then 2 to the n, I gave you very small n values. I never gave you a formula with more than 10 variables, and so it's going to be fast. But once you have like 50 variables in your formula that you want to sat solve, it's going to take you longer than I've been alive to solve it. Crazy. And then that just keeps doubling, so you end up like at some point taking longer than the amount of time the universe has existed to run the algorithm, and of course that's never going to finish. Okay, so this is just a PSA to keep your algorithm running times within these ranges, maybe n squared at the most if you have to. Okay, and then there's a cool anecdote that maybe you've heard about like a year or two ago. The game GTA 5 had a n squared algorithm that ruined the loading times of the game. And actually that was not an optimal algorithm. Somebody went and modified the code and fixed it, just somebody who owned the game. And then the makers of the game were like, oh yeah, let's change it to be like that. That's much better. And then the loading times got better. So this n-squared algorithms can ruin your day, and it happens in practice. Okay? So that's something to keep in mind. Let's keep on going. Time for you now. So I want you to try this. See if you can figure out the asymptotic growth, so do a runtime analysis, in the worst case, so the worst that this could possibly run, of the following algorithm. You don't have to fully understand it as long as you're understanding how many iterations these things might take, but what it's supposed to do is find a maximum subsequence sum, so take a bunch of elements and find the biggest subsequence of those elements that gives a large value. So your job is to find the worst case, and let me talk a little bit more about the algorithm to give you an idea. So let's say that we had a sequence. This is getting input that is a sequence and elements, and so here's my example sequence for us. Let's have 5 elements. 1, -2, 3, 5, -7, and here are the indices. I guess here they start at 1, so let's start them at 1 here. Why not? 1, 2, 3, 4, 5, like A1, A2, A3, A4, A5. And the goal is to find a subsequence, which is a bunch of contiguous elements, like here are a bunch of contiguous elements, and then figure out their sum. So the sum of this sequence from here to here is 5 plus 3 plus -2, which is 6. And then we are looking for the maximum subsequence over all of these that gives us the biggest number, and it looks to be this one. These 2 elements right here, that's the biggest subsequence of consecutive elements that you can add together and get a large number. So 8 is the maximum subsequence sum, and that's what this algorithm's trying to find. Okay, so see if you can, with that, analyze it. All right, so assuming you're back now and you gave it a good try, let us talk about it. So remember, you're getting as input a giant sequence of n elements, starting at 1 for no good reason. And let's see what happens when we run it. So I've made this nice new slide with the same algorithm on it so that we can talk about it. And let's go through it. So we need to figure out like all the different things that are happening, all the different times, and then add them up. So here's like the first line of the program. Max sum gets 0. That's an assignment. It is constant time. Okay. Then we have a loop that's going to iterate n times. We'll worry about that in a second. And then for the body of it, we have constant work. That's an assignment. Then we have another loop, which we'll sadly have to worry about, that goes from I to n. Interesting. And then its body is constant work because it's doing an assignment and an if statement with potentially an assignment. That's at most 3 things, right? So that's constant. And then at the very end, there's a return statement. Excuse me. There's a return statement, and that's constant time to return something. So now we need to worry about these loops. Let's figure this out. Because it is subtle, you might be able to assume like this is going to take at most n times to run its body. Like it's going to run n times because I will start at 1. But that's the first time. The first time this loop runs, it goes n times. And then when I gets incremented to 2, then it goes n minus 1 times the second time. Then the third time this iterates, it goes n minus 2, n minus 3, n minus 4, n minus 5 times, all the way down to like 1 time. And so we need to talk about that. You can't really, well, you can assume that it is in the average O of n, or theta of n, but I need to tell you why. We need to actually do the real analysis for once of this. Okay, so let's talk about it. Like, how many times is this loop going to do its work? Okay, let's talk about that, and let me, close my email. So let's draw over here. Let's do some stuff. So what I just said was, like, when I is 1, this inner loop is going to iterate n times. When I is 2, it's going to go 1 less time, right? It'll go from 2 to n, which is n minus 1. When I is 3, it'll go n minus 2 times. So we need to think about this, okay? And it is running constant work on the inside, so that's fine. We don't have to worry about that. There's just going to be a constant out in front of that. That's not a big deal. So we need to figure out what's happening here, okay? Because in the end, let me use rainbow for this. Like, this is going to run n times. So this line is going to run n times. That's now theta of n. And then we need to figure out how much work this is doing. That's our job right now, okay? Because then we'll have the amount of work done by the whole loop, okay? So we've just learned that this is going to run n times on the first iteration, n minus 1 times on the second, n minus 2 times on the third, each time doing constant work in its body, okay? So let's analyze that. Let's figure this out, because in total, that means the amount of work that is being done, the amount of times that loop will iterate, is going to be n plus n minus 1 plus n minus 2 plus ... all the way to 1, right? Because it's going to go from like n to n, which iterates 1 time. And this is a sequence that has a closed form, we say. There is a formula to sum all these together. Do you remember it? It's going to be n plus 1. It's like you take this and you add it to itself backwards. So it's n plus 1. How many times? N times. Over 2, because we double counted. So that is equal to, let's see, n squared over 2, so 1/2 n squared, plus, and then there's an n, 1/2 n. Oops, 1/2. And then there's constant work in front of that. I guess we don't need to get there yet. So this whole thing, how many times is the loop going to run? Theta of n squared times. That's why you can actually assume that this is like n. It does work out, but now I wanted to show you why, okay? So all of this code the body of this loop is going to run on the order of n squared times, and then it does constant work for each of those iterations, so it's still theta of n squared for all of that work in that body of that loop. Theta of n squared. Okay, we did it. So that was our job. We had to figure out how many times is this going to execute its body. How many times? And we figured it out. On the order of n squared times. So, adding it all up now, for the whole algorithm, we do constant work plus, remember that this is ranging over from 1 to n, we did this n times, so theta of n work, so constant plus theta of n plus theta of n squared for that whole thing over each iteration of the outer loop, so n squared time plus another constant work. So in total, the limiting factor, the thing that matters most, is that n squared. So the whole algorithm is theta of n squared time. Do you see how I did that? So that is how you analyze a nested loop that kind of depends on the outer loop. Okay? That's a little bit tricky. So do yell at me if you have any questions about that. But I think we're good to keep going. So the last part of these slides is finite state machines. Let's talk about those. Okay? Let us begin. So this is a very nice topic. I like to teach it in CSCI 40, but we're ready to learn about them in a lot more detail now. Okay? So what in the world is a finite state machine? It's just a very nice way of thinking about computation. If you can model something as a finite state machine, it becomes a very nice program, an easy program to write. All right, so a finite state machine, or an FSM for short, is just a model of computation. It's a model of some system. It gets very vague. What it does, though, or what it has, is a bunch of states. Here are 2 states, for example, and then it has transitions to move between states. So like, if you see a 1, we transition from the even state to the odd state. And if you're in the odd state and you see a 0, you go to the even state, things like that. Okay? So a finite state machine also has to have what's called a start state. Like, this is going to accept input, so we need to know which state it begins in. That's what this arrow is saying. So this is where it starts. It starts in the even state, apparently, this one. This one starts in the Q0 state, whatever that means. And then, optionally, if you only want to do special things, like when the input is over, you want to know something, like did this thing work or not, you can have what's called final states as well. Those are optional. Final or accepting states. And that's when you put 2 circles around your state. This is just a normal state. This is a final state, or an accepting state. Okay? So for example, this is really a finite state machine that accepts only even binary strings. Okay? And I'll give you an example of that on this slide. So I guess I'll give you an example of both. And then this one is a finite state machine that is like for a vending machine. It only gives you stuff. It only gives you like food or a drink if you put in 20 cents. Okay? So you have to get to this state to actually give something. Okay? So that's what it looks like. And this is kind of helping you model something that has output as well as taking input. So the input is like the coins. You put in a nickel, you go to the next state. You put in a nickel, you go to the next state. But there's also output, so that's what these slashes are meaning. Put in a nickel, there's no output still. Put in a nickel, there's still no output. One more time. You put in one last nickel, that gives you, I guess, 25 cents. Then it's going to give you something back. It returns to you a drink. Okay? So let's talk about those in detail and run these state machines. Let me show you how they work. Okay? So this one is keeping track of even or odd binary strings. So strings of binary numbers, so just a bunches of zeros or ones. For example, here is a binary string, 0, 1, 0. That means it's secretly 2, right? Because this is the 1's place, this is the 2's place. That's really the number 2. And starting zeros don't really matter. So let's run the state machine with this input. You give it 1 digit at a time, 1 bit at a time from left to right, and we see if it ends up in the even state. If so, it's an even number. Okay? So let's do this. Let's run it with this. We start in this state, we start in the even state. and then we give it a 0. Oh, it stays in the even state. The 0 number that we've built up so far, the number just 0, is even in fact. And then we give it a 1. That's our next input to the state machine. And so in total, the number that we just gave is the number 1, which is odd. And so we are correctly transitioning to the odd state. The number that we've built up so far in terms of input is odd. And so we are here now, ready to take more input. And then we get a 0, and that brings us back to the even state. So we had a number that ended in 0, which means we just multiplied whatever this last number was by 2, which makes it even, right? That's what binary gives us. And so we end up in an even state, and it accepts the string because we ended in an accepting state. Okay? So yeah, this is because we started out with just 0. 0 base 2 is 0 base 10, right? Which is even. That's totally fine. And then 0, 1 that we built up halfway, base 2, is just the number 1 base 10, right? And that is, of course, odd. So yeah, this state machine, you give it as big of a number as you want, 1 digit at a time, 1 bit at a time, then it will tell you if that number is even or odd, because that's how you look at a binary string. Just look at the last digit, really. That's all you need to care about. And then this one, let's see. Or let's do some more. Let's do one that's odd, like 1, 1. If I give 1, 1 to this state machine, it goes here, and then it stays in the odd state, right? Because that is 3 base 10. That doesn't work. And then 1, 1, 0, though, if I gave that, it does 1, 1, 0, because that is 6. And that is really even. It's working. And then this one is, again, you having output as well as input. So here's how the book is going to write it. You take inputs that move you, that transition you between states, and you also give out outputs, potentially, once every transition gets made. Okay? So at like the start, this is a vending machine that takes it takes nickels, and it needs 25 cents to give you back something. It's a very cheap vending machine, apparently. And here's your start state. The Q sub 0 means that you've put in 0 cents so far. And so you start here, having given no money. Then you put in an input of a nickel, and that moves you to the Q5 state. The state machine is remembering that you have put in 5 cents worth of money so far. And then there is no output yet because you haven't given enough. Okay? So there's potentially no output across transitions, but eventually there will be output. So you give it another nickel, you go here, another nickel goes here, still no output. Another nickel goes here, still no output. One more nickel, that's 25 cents, and that actually finally outputs something, your soda or whatever. Okay? So that is a state machine that has outputs. Hopefully that makes enough sense. And now let's formalize this. So how can we use math? How can we use set theory, because that's supposed to be how we define everything. How can we make these things? How can we make finite state machines and define them mathematically? Okay? So here's what you need to get all technical. You need 5 things. A state machine is a tuple of 5 things, called a 5-tuple or quintuple, whatever you want to say. It takes a Q set, takes a Q0, Q naught. It takes an I, an A, and delta. Okay? So that is just a normal finite state machine. If you have a finite state machine that produces outputs, you also need another set of outputs instead of accepting states. So let's talk about this 5-tuple. What is Q? What is Q0? What are all these things? Let's do it for this even odd state machine. Okay? So to define mathematically in full what a state machine is, you need Q, the set of states. That makes sense. Definitely need that for a state machine. So there are 2 states in this one, even and odd. Oops. So the Q for that state machine is even and odd here. Then, to define the state machine, you need a start state. That always is necessary. Q0, Q naught is, well, we start in the even state for that particular state machine, right? That's what this arrow is saying. Then we need inputs, I for inputs, finite set of input actions. What will drive the state machine? What kind of things move it around, cause transitions? So for this state machine, it accepts binary strings one bit at a time, so single bits are the input to the state machine, zeros or ones. That's what moves it around. Yeah, not too bad. This is just what you need to define a state machine. And then we have A, potentially, if this is a state machine that has final states, you have accepting states. That's a subset of the original state's Q. So the accepting state for even things is just the set containing the even state only, right? That's what we want it to end in, which says that the number that we've built up inside of the state machine is even. Yeah? And then finally, we have to talk about these transitions and how they move us between states. That's the last piece of the puzzle. So the very last thing is a transition function, delta for change, right? Little delta though. And it takes a pair of things. It takes your current state Q. This is your input, this is the output, right? It's a transition function. It takes your current state and it takes the input. So at this state, you take this input and you move to potentially a new state. Maybe you stay in the same state, but you need to say which one. Okay, so that gives you a new state. And that is all the transition function is. Let's do that for this one. So delta is, what is a function but a set of input-output pairs? So for example, this delta takes, if you're at even and you take 0, you remain in even. Okay? So this is how you write this as a function. If you take the input even 0, even comma 0, that pair, you're still in the even state. Yeah? That's how it works. And then likewise, if you're in the even state and you see a 1, then you're supposed to output odd, because that's the new state you go to. So that's how you can define the function. And then if you're in the odd state, you see a 0, you go back to the even state. And finally, if you're in the odd state and you see a 1, you go to, you stay, because you just saw another 1. You stay in the odd state. So that's how you define the transitions between states. And that's all you need to formally specify exactly this state machine. I hope that makes sense. That's just what you need mathematically to make this all happen. And so I think with that, I would like you to give this all a try. So here are 2 finite state machines, 1 and 2. I would like you to run these inputs in each of these machines. Okay? Give them these input strings. Apparently they take binary strings too. And have them start in the start state, go through that string, and tell me which state you end up in. Okay? Also, tell me if that state that you end up in was a accepting state, whether or not that last state, I shouldn't say final state because that's a loaded term, right? Whether or not that last state that you end up in is an accepting state. Okay, so try that. Run each of these in each machine, and then we'll talk about it. All right, so you have finite state machine 1 and finite state machine 2. And what I should do is give us room to write right there. So finite state machine 1, finite state machine 2. Let's run this in finite state machine 1 and 2. So you start here, you take 1, 0, 3 zeros, 0, 0, and then a 1, and then a 1. So we end up in B, apparently. We end up in B. Is that a accepting state? No, it doesn't have those 2 things. C is the only accepting state. It's the only final state. So this is not an accepting state. For finite state machine 2, if we do this one, you start here in B. So this is 1, 0, 0, 0, 1, 1. So I can take anything and stay in the state A. So that ends me up in A, which is an accepting state. Cool. And let's do that for each of these now. So for 0, 0, 0, 0, this one is 0, 0, 0, 0. It looks like it keeps us in D, and that is not an accepting state. It's not a final state. What about this one? This is 0, 0, 0, 0. Yeah. As long as that one got 3 zeros, it's happy. So that ends us up in A, which is, again, an accepting state. Cool. 0, 0, 1, 0 now for the first one. 0, 0, 1, 0. Oh no, it doesn't like. This one doesn't like that starting 0. Oh man, that gave us back to D, which is again not accepting. What about this? 0, 0, 1, 0. Oh no, we did not get where we wanted it to be. We ended up in C, which is not an accepting state. And then finally, 1, 1, 0, 0. Let's do that. 1, 1, 0, 0. Finally, finite state machine 1 is happy. That gives us C, which is an accepting state. What about this one? 1, 1, 0, 0. That works. That seems to work. Oh wait, no, I think I did that totally wrong. Sorry. Let's try it again. 1, there we go. 1, 1. Yeah, I should have stayed there. 0, 0. I knew something was wrong. So that's D, which is not correct. There we go. So yeah, that's just running the state machine. If you have one, it's not too hard to run it. The complicated thing is like, how did you come up with the fact that this is going to keep track of evenness or oddness? It's very elegant, though, if you can make a state machine. So that's the end of these slides. Let me go and prepare the next ones and see how much time we have left for them. And I will cut to that in just a second. Okay, these next slides are about induction and recursion, which are very fun topics, and hopefully you will learn to love them as well. If you, for example, hate recursion right now, it will become a lot clearer by going through these slides. So let's start out with a topic that you already know about. Let's just try and mathematically define sequences of things, right? So, like, I have a sequence of numbers, it goes in some certain order, okay? So how can we define that mathematically? A sequence, it's just a function. We can define a sequence as a function whose domain is a bunch of consecutive integers. And so let's use the Fibonacci sequence, which we should be hopefully familiar with by now, to demonstrate this. So remember that the Fibonacci sequence, I guess, depends on who you ask, but either the first two numbers are 0 and 1, or the first two numbers are 1 and 1. Let's pretend that the first two numbers in the Fibonacci sequence are 0 and 1 for the sake of this example. And so the Fibonacci sequence, it goes like this, right? It goes 0, oops. It goes 0, 1, and then the next element of the sequence is the sum of these two previous ones, right? It's 0, 1, 1, then 1 plus 1 is 2, 2 plus 1 is 3, hopefully it's all coming back to you, 3 plus 2 is 5, 3 plus 5 is 8, and so on and so forth. That is the sequence, and you can represent that mathematically as a function, okay? So here's the Fibonacci sequence, like the 0th element is 0, the 1th element is 1, the element 2 is also 1, element 3 is 2, element 4 is 3. This is just a function taking which index you want to the value at that index, right? That's not too bad. So it's just a function whose domain is the set of consecutive integers. So for example, these are the domain. Here, this is like the value of the function. That's what it goes to. But the domain is, this is the 0th element. This is the 1th element. 2, element 3, element 4, element 5, element 6. And those get mapped to the values of those indices for that sequence. So like, if you give 2 to this sequence function, it gives you back 1, because that's the element at that element at that index of the sequence, yeah? So yeah, just make it a function. The domain is all the indices that you want to access for the Fibonacci numbers, so it's all the non-negative numbers, integers, and then like the result of your function that you're making to represent the sequence is just these. F of 0 is the first element, f of 1 is the second element, f of 3 is the 2, 3, 4th element, something like that. So you see how that works? Just make it into a function. That totally works out. So each element, each SI, FI, whatever it is, in a sequence is called a term, right? This is a term. Like, for example, this is 0, 1, 2. This is like the third term in the sequence, in the Fibonacci sequence. And the index here is 2, okay? index 2. So the index tells you where you are in the sequence. Sometimes they start at 1, other times they start at 0, because we're computer scientists. Okay, so instead of saying, in summary, instead of saying f0 equals 0 and defining the sequence like this, mathematically, you can think of it as a function that accepts that 0 and gives back the value of that sequence at 0. Okay, that is the goal. So that is how you can mathematically define a sequence. Hopefully that seems useful to you, and that will let us talk about cooler things. So here's a nice meme to give us a little break, and then we're going to come back and do some more definitions now that you've sufficiently enjoyed yourself. So sadly, as you start a new chapter, it's always a game of lots of definitions, so let's get those out of the way so that we can have fun later. Let's talk about kinds of sequences. Okay, a sequence, we say, is increasing if you have two consecutive indices. If you consider every possible pair of consecutive indices, k and k plus 1, it's always the case that ak is less than ak plus 1. I hope that makes sense. So this is trying to say, no matter where you go, like pick out any two elements of your sequence. Maybe here we are, this is ak, this is ak plus 1. Don't worry about the rest right now. You're eventually going to try them all, though. It better be the case that a of k, if it's 42, is smaller, strictly smaller than ak plus 1. So this is like 44. And so hopefully this is not too hard to understand. Like, this just means that every next element better be bigger than the previous one. That is kind of, that's the dictionary definition of increasing, right? Never getting smaller. So 0, 1, or always getting bigger is the right word. So 0, 1, 42, 43, 47, 55, ... That's an increasing sequence, okay? Always getting bigger. Every two possible pairs that you look at every possible pair, this one and this one, this one and this one. You give them all a chance at being k and k plus 1. You confirm that this is always true for each of those pairs, okay? That makes sure that it's an increasing sequence. On the flip side, if you introduce an equal to in your less than, you get what's called a non-decreasing sequence, okay? And that's when, looking at every two consecutive indices, k and k plus 1, it's not the case that it's strictly less than. A of k is not strictly less than a of k plus 1, but it's never getting strictly small, or it's never getting, yeah, k plus 1 is never smaller, sorry. So it's always not decreasing, though it might be staying the same for a little bit. That's what the equality gives you. So here's an example of a non-decreasing sequence. Like, it can stay at 0 for a little bit, it can stay at 1 for a little bit, it can stay at 4 for a little bit, it can stay at 4 for a while if it would like to. But the next element needs to be equal to the previous one or bigger. That's all it's saying here. All of those pairs, 42, 43, ... That's totally fine. That is a non-decreasing sequence, okay? Then we have the opposites of those. So a sequence is decreasing if it's always getting smaller, the next element, always getting strictly smaller. So like 4, 2, 1, negative 17, negative 42, ... Always getting strictly smaller. Every two consecutive indices, the values there always have that relationship. And I'm pretty sure you can understand now what non-decreasing means. It's just you introduce that equals to, the next element is smaller or equal to the element. So it can stick at the same element for a while, but it has to eventually start getting smaller. If you pick a different number, that is. So that is non-decreasing. That is the, oh sorry, excuse me. I shouldn't have said non-decreasing, it's non-increasing. We already did non-decreasing. So yeah, this is non-increasing. It's always getting smaller or staying the same, okay? Whatever it's doing, it's definitely not increasing, okay? So those are the definitions that I wanted to talk about. Let's check the time. I think that is good enough for now. We'll come back next time with some more terms. We'll talk about things that you've learned in a math class before, so like geometric or arithmetic sequences. We'll talk about that in detail, and that will eventually lead us into the ideas of induction and, like, formally, like what recursion means. So look forward to that in the next lecture, and I'll see you then.